All right. Hey, everybody. I want to tell you about calibration in about 15 minutes. This is, for those of you watching online, a tutorial that I will give at the Fox workshop on calibration this coming Sunday. So to get you into the right frame of mind, I want you to think about probabilities, real probabilities. Okay, and I'll walk you through 3 examples. So suppose I asked you, what is the probability that if I flip a fair coin 16 times, I get exactly 9 heads? Well, this is a really concrete probability. This is something you can really get your hands on. There's at least 2 ways you could do it. We've got a very good mathematical model that maps well onto reality. So you could just sit down with a pen and paper and you could, within the mathematical model, compute this in closed form. Alternately, you could just conduct the experiment repeatedly. A bunch of times. You could flip a coin 16 times in a row. You could count how frequently you get exactly 9 heads, and you could take the average. And if you did this enough times, you would get a good empirical estimate for this probability. And reassuringly, it would agree very well with the number you computed within the mathematical model. Now, there are some more troubling uses of probability. I could ask, what is the probability that Kamala Harris wins the 2024 US presidential election? Okay, here are the probabilities that Polymarket gave yesterday. Well, this is a more difficult question. Certainly, we don't have a mathematical model for this. It's not something you can compute analytically. And maybe if we posit a probabilistic model of the universe, like, maybe there are like quantum mechanical effects, so that if I run the universe repeatedly from now until, a week from Tuesday, maybe Donald Trump wins some fraction of the time and loses some other fraction of the time. And maybe it makes sense to have a belief, that the probability really is 62.5%. But even so, it's not like the kind of thing we can get our hands on. We don't have the ability to run this experiment more than once. Okay, so these probabilities are slightly more troublesome. And then even worse is sort of the kind of thing people do when they ask for confidence scores for large language models, for example. Okay, so maybe ChatGPT says that the leading cause of death globally in children under 5 years old is diarrheal diseases. What is the probability that that is correct? Well, I mean, this isn't something that can have some platonic probability between 0 and 1. Like, it's either true or not, and it's not even unknowable. Like, I could look this up on Wikipedia with some additional knowledge. I would know whether it was true or false. So speaking of a 27% chance that this is correct doesn't even really make sense, but it would still be useful to have confidence scores for large language models. Okay, so what should we do with all of this? And one thing you can do is you can ask for simple statistical conditions on sequences of probabilistic forecasts to hold that are basically self-consistency conditions. You can ask that the forecasts be self-consistent in various ways. And calibration is one such self-referential consistency condition. Okay, so calibration goes back at least to David's work in the early 80s. He was using it to try to build a frequentist foundation for probability theory. And you can do all of this also in online adversarial settings, but suppose for now that we have a distribution on labeled examples. There's some distribution on features and binary labels. So if I have a model for producing forecasts given features that purport to be the true probabilities that the label is 1, conditional on the features. Okay, well, we've seen examples that might make it hard for us to check whether this is true, but at least we could try to subject these forecasts to sort of simple hypothesis tests that would falsify the claim that they are real probabilities, and calibration is one such test. Calibration asks that the forecasts be statistically unbiased, conditional on the forecasts themselves. Okay, so conditional on predicting a 20% chance of rain, It should really rain 20% of the time. Real probabilities would satisfy this condition. We can't check if we have real probabilities, but we can check if our probabilities are unbiased in this self-referential way, and that's calibration. Now, okay, we're never going to get perfect calibration, and even if we could, we can't like measure it with finite samples to verify that it's perfect. So we need to talk about approximate calibration error. There's many ways to do this. It's an area of active research. But a classic way is expected calibration error. On each level set of our predictor, we can compute what is the statistical bias of our predictor, conditional on lying within that level set. And then we can just average these bias terms, or the absolute value of the bias terms, over the level sets weighted by the frequency of the level sets. That's the expected calibration error of a model. There are some disadvantages of this. It's discontinuous in the predictions. It turns out to be inconsistent with getting the right rates in online settings, but this is a standard measure and it has some nice things going for it as well. So why should we like calibration? Well, in my view, the most interesting thing about calibration is that it provides a straightforward and trustworthy interface between predictions and decisions. And here's one way of formalizing that. Suppose I've got a model that has expected calibration error at most alpha. And now imagine that downstream of the model, there's some decision maker who actually needs to take some action from some action space A to interact with the world and has some utility function. The utility the decision maker gets depends both on the action that he takes and on the realization of the label. And it maps to a number between 0 and 1 that he'd like to make big. Now, one thing he could do with our forecast is he could pretend that it was correct. He could pretend that when we predicted, a 75% chance that the label was 1, that the label really was drawn from a Bernoulli distribution with bias 75. And he could choose the action that maximizes his expected utility under the presumption that our prediction was correct. Or he could do anything else. He could take any other policy mapping our predictions to actions and play that. Well, what should he do? Well, this theorem says that no matter what his utility function is, we didn't need to know what it was when designing the predictor, no matter what his utility function is, he should just best respond to our predictions. That's better than any other policy mapping predictions to actions, at least up to twice the expected calibration error. Now, okay, don't get too excited about this because there's like an important caveat. At least in distributional settings, there's many ways to be calibrated, one of which is not very useful. A constant predictor that always predicts the label mean is calibrated because the self-consistency conditions that calibration asks for are self-referential. They condition on the level sets of the predictor, and if you just predict the mean, there's only one level set. So it just asks for the predictor to be marginally unbiased. And such a predictor can't possibly be very useful. So how does this square with the decision-making guarantee I just told you about? Well, the comparison class of policies were policies mapping predictions to actions. They were self-referential. So if our predictor was a constant function, the only promise it gave was that our decision maker does better best responding to this constant function than they would playing any other fixed action. But it's not a very strong guarantee. It doesn't tell us anything about how well they do in comparison to policies that can depend on context. And that's sort of inherent because calibration doesn't require on its own that you look at context. You can ignore context and predict the label mean. So if we do want to compete with policies that depend on context, we need a stronger guarantee. Here's one stronger guarantee called multicalibration. It asks for calibration to hold conditional in various ways on external context. So for example, we could fix a collection of grouping functions, each of which is some subset of the feature space. These groups don't have to be disjoint. And then we could define for each grouping function the conditional distribution that sort of conditions on membership in this group. Okay? You could generalize this to weighting functions that reweight the distributions, but this is enough for now. Then multicalibration asks that our predictor have low expected calibration error, not just overall, but like on each of these conditional distributions. Okay, so it's just a bunch of simultaneous bounds on the expected calibration error, one for each of these conditional distributions. And the way we're going to parameterize it is that sort of the less frequent the conditioning event is, the weaker the bound we will require. As a result, this is going to be something that we can do efficiently from small amounts of data. So multi-calibration is interesting for many reasons, but here's one connecting it to downstream decision making. Suppose you've got some class of policies that map context to actions now. These are the policies you'd like to compete with. Let's now define groupings of the feature space, defined by the level sets of these policies. For every policy and for every action, there will be a group corresponding to all of the feature vectors that cause that policy to play action A. Okay? So now it turns out that if you're multi-calibrated with respect to this class of groupings, then once again, if we have a downstream decision maker who could have any action space and any utility function that we don't need to know, and now we compare with benchmark policies that are allowed to choose actions not only as a function of our prediction, but also as a function of the actions suggested by any one of the benchmark policies in this class P, we can again promise that the utility of the downstream decision maker who ignores all of this complexity and simply best responds as if our predictions are correct, well, that'll be better than anything he could have done as a function both of our predictions and of any of these benchmark policies. Special case of this is that he does better than playing any of these benchmark policies, and now his loss that comes from calibration error is just alpha times the multi-calibration error multiplied by the number of actions he has. Okay, so this is related both to the omni-prediction literatures and the literatures on forecasting with downstream regret. Okay, so some useful stuff to know for this workshop. First of all, it's possible to do these things. It's possible to maintain calibrated and multi-calibrated predictors, not just in the distributional setting, but in online adversarial settings, which is, where I think the most interesting implications for decision making are. And you don't have to give up on accuracy, at least as measured by squared error or any other proper scoring rule. Imposing these calibration conditions is only accuracy improving. But the way you measure calibration error is important, and in terms of the rates you can get for expected calibration error, the story is complicated and pessimistic. See Prince Will's talk. For this and other reasons, we might want to think about better measures for approximate calibration error, and this is something that Parikshit's going to talk about. And if, in particular, we're most interested in these sort of downstream loss minimization problems, then maybe we should think about calibration measures that are sort of targeted specifically at downstream decision makers. And this is what Michael Kim is going to talk about, and Yifan has a talk in the main program of Fox about this. And calibration is useful for other stuff as well. In general, whenever real probabilities would be useful, you can go through the exercise of asking whether you really needed real probabilities or whether sort of a modest number of tractable calibration guarantees would be enough. And oftentimes it is. Natalie's going to talk about an application of this to sort of tractable generalizations of Oman's agreement theorem. Okay, and there might be some tasks for which calibration isn't desirable. Adam's perhaps going to talk about when calibration of language models might sort of necessitate the fact that they hallucinate. Okay, so my 15 minutes is up, but if you want to learn more than 15 minutes about calibration, I've taught several courses on these kinds of things. I've got lots of lecture notes and course recordings at these two websites, uncertaintyclass.com and mlgametheory.com. So thank you.